In this video, we'll review the different strategies for testing a series for convergence or divergence. Now, the order that I have these listed here are not necessarily the order of tests that you perform. It's going to take a little practice to know when to use which test. This is just a quick review of the different tests we could perform. First is the test for divergence. If we can somewhat clearly see that the limit as n approaches infinity of our sequence may be something other than 0, then we can apply the test for divergence. If we clearly have a p-series, that is 1 divided by n raised to the p, then the series will be convergent if p is greater than 1 and divergent if p is less than or equal to 1. Another familiar series is the geometric series. That will look like a times r raised to the n minus 1 or a times r to the n. Here, if r is less than 1, then it's going to diverge, and if r is greater than or equal to 1, it will converge. Another thing we can do is the comparison test. This is when we have a series that looks similar to a p-series or a geometric series. Maybe we can directly compare the original with the geometric or p-series, or maybe we can use a limit comparison. Alternating series will be in the form -1 raised to the n minus 1 times b sub n, or -1 raised to the n times b sub n. If we have this situation, we often use the alternating series test. We also have a ratio test. We use this test typically when we have factorials in the series, or if we have other products, including a constant raised to the nth power. The root test is used typically when we have an nth power as well. And the integral test will be used if we can write the series as a function and integrate that function. Now we need to make sure that f, the function, is continuous, positive, and decreasing in order to use this test. Once again, that is just a brief overview of the different tests. This is not necessarily the order that you perform the tests. It's going to take a little practice to know when to use which one. In this example, we have two similar looking series. Let's test each one of them for convergence or divergence. This first one we can rewrite as the sum from n equals 1 to infinity of 1 divided by 5 raised to the n. This we now know is a geometric series. And r is equal to 1/5, that base that's being raised to the nth power. Since the absolute value of r is equal to 1/5, and we know that that is less than 1, we can say the series 1 divided by 5 to the n converges. Notice our next example looks very similar to the first one, but this one is not a geometric series because we have this extra plus n in the denominator. But maybe we can do a comparison. Let's start with the sequence that we're given, and what happens if we look at just the dominating part there. Look at the 1 and the dominating part of the denominator. We're looking at 1 divided by 5 to the n. Notice what we did. We made the denominator smaller. If the denominator is smaller, this fraction is bigger. And more importantly, we know something about this bigger fraction. We know that this sequence or series converges because it's geometric, as we saw up here. So if we have a bigger geometric series that is convergent, then the smaller series must also converge. So we can say that the sum from n equals 1 to infinity of 1 divided by 5 to the n plus n converges by the direct comparison test. In our next example, we again have two similar looking series. Let's test each one for convergence or divergence. Notice where 3 to the n is located. In this example, 3 to the n is in the denominator. In this example, 3 raised to the n is in the numerator. Let's use that as an indication as to how to approach these. In this example, since 3 to the n is in the denominator, it's probably a good idea to use the ratio test. We'll have the limit as n approaches infinity of the absolute value a sub n plus 1 divided by a sub n. Limit n approaches infinity. The next term in the sequence would be n plus 1 divided by 3 raised to the n plus 1. And we want to divide that by the current term, n divided by 3 to the n. Next, we'll just rewrite that. Copy the top part. And we're going to multiply by the reciprocal of the bottom fraction, 3 to the n divided by n. Next, again, just rewriting this, we can rewrite this first denominator using exponent rules. We'll have n plus 1 divided by 3 to the n times 3. And we'll just copy the second fraction. From here, we can reduce 3 to the n. Will go away. And notice we have a constant. I'm going to pull that constant out front. So we have 1/3 limit. N's getting really big. And we have n plus 1 divided by n inside the absolute value. At this point, limits at infinity, we can divide the top and the bottom by n. That is the highest power of n that occurs in the denominator. We now have 1/3 limit of 1 plus 1 over n divided by 1. Now evaluating the limit, 1/3 times 1 plus 0 over 1. Here we get 1/3. And that we know to be less than 1. So, the original series, n equals 1 to infinity, of n divided by 3 to the n, is absolutely convergent. And if it's absolutely convergent, we know it to also be convergent. And that's by the ratio test. This next example, again, is very similar to the previous one, or it looks similar anyway. But notice right now, just intuitively, as n gets large, as n approaches infinity, the numerator is exponential and the denominator is linear. That means the numerator is going to grow much faster than the denominator. So my intuition says that this is going to diverge. Let's use the test for divergence. We have the limit as n approaches infinity of 3 to the n divided by n. We'll need to use L'Hopital. So we'll take the derivative of the numerator, 3 to the n ln 3, divided by the derivative of the denominator, 1. And we can see that this is simply going to be infinity. So That tells us that the original series diverges by the test for divergence. In this example, we have the series of n squared minus 1 divided by n cubed plus 1. This isn't exactly a geometric or a p-series, but if you look closely, it's close to a p-series. Look at the dominating part of the numerator and denominator. We have n squared over n cubed. Let's think about that. N squared minus 1 divided by n cubed plus 1, and let's compare that to the dominating part, n squared over n cubed. Well, n squared over n cubed is really 1 divided by n, which is a p-series, or more specifically, the harmonic series. Let's call this b sub n, and we'll call the original a sub n, and we can use a limit comparison. Limit n is approaching infinity of a sub n divided by b sub n. Limit, we'll copy a and divide that by b. We can now rewrite this. Copy the first fraction, and we'll multiply by the reciprocal of the denominator. Limit of n cubed minus n divided by n cubed plus 1. From here, we'll divide by the highest power of n that occurs in the denominator. So divide the top and the bottom by n cubed. Limit of 1 minus 1 divided by n squared divided by 1 plus 1 divided by n cubed. Now evaluating the limit, 1 minus 0 divided by 1 plus 0 gives us 1. And that we know to be bigger than 0. And since the limit is bigger than 0, we know that both series converge or diverge. Which one is it? Look at what we chose for b sub n. B sub n is the harmonic series, which we know diverges. So since that one diverges, the original must also diverge. N squared minus 1 divided by n cubed plus 1 diverges by the limit comparison test. In this example, we have the series of n minus 1 divided by n cubed plus 1. Initially, it's not a p-series, but maybe we can compare it to one. Again, looking at the dominating part of the top and the bottom. N minus 1 divided by n cubed plus 1. If we remove the negative 1 from the numerator, think about what that's doing to the fraction. It's making the fraction bigger. Well, what else will make the fraction bigger? If we remove the plus 1 from the denominator, that will make the fraction bigger. And we know that this is 1 divided by n squared, which is a p-series. And in this case, p is equal to 2, which is bigger than 1, which means it converges. And if we have a bigger sequence or series that is convergent, then the smaller must also be convergent. So we can say the original sum, n equals 1 to infinity, n minus 1 divided by n cubed plus 1 converges by the direct comparison test. In the next example, notice that we have negative 1 to the nth power. That's a good indication that we'll probably be using the alternating series test. So let's start by denoting b sub n is n squared minus n divided by n cubed plus 1. And to help us with the two steps that we need to show, let's simplify this. Notice that we can factor the numerator. It's a difference of squares. And we can also factor the denominator. It's a sum of cubes. So simplifying this, we get n minus 1 divided by n squared minus n plus 1. Next, we need to show that the limit as n approaches infinity of n minus 1 divided by n squared minus n plus 1 is 0. So we'll divide the numerator and the denominator by n squared. We'll get the limit of 1 over n minus 1 over n squared divided by 1 minus 1 over n plus 1 over n squared. And we can see that this limit is 0. The next thing we want to know is it decreasing? Let's test the first derivative. So if we call this f, f prime is then the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Simplifying this, we'll get negative n squared plus 2n divided by n squared plus n plus 1 squared. And in order to show where f prime is decreasing, we want the derivative to be less than 0. Notice that the denominator is always positive. We can then focus on the numerator. We'll factor out a negative n, leaving us with n minus 2. And notice that this is negative for all n greater than or equal to 1. So we have what we need now. It's decreasing, f is decreasing on the interval from 1 to infinity. So, by the alternating series test, we can say that the original series is convergent. In this example, it may not be obvious right away what method we need to use. It's clearly not a piece series or a geometric series, and it's not an alternating series like we saw in the previous example. Look at the sequence and think of it as a function, and see if that function would then be easy to integrate. It looks like we might be able to integrate this. Notice that the exponent on the e, if we take its derivative, it'll look something like n squared. So we might have some u substitution on our integration happening there. So let's think of our function as x squared e to the negative x. And remember that in order to use the integral test, we need to know two things. We need to make sure that our function is continuous, and it is. We need to make sure it's positive, and it's also positive. We need to make sure it's decreasing on the interval from 1 to infinity. That one may not be quite as obvious. So let's take the derivative. We have x squared times negative 3x squared e to the negative x squared plus e to the negative x cubed times 2x. And then, simplifying this, we get 3x to the fourth e to the negative x cubed plus 2x e to the negative x cubed. Then we can write that as x. Let's factor out that x. Negative 3x cubed plus 2. And we'll push the e to the denominator. And we want to know where that is less than 0 to make sure it's decreasing. We'll focus on the numerator, more specifically the second factor. We'll get x is the cubed root of 2/3, which is roughly 0.87. And so it looks like we are decreasing from 1 to infinity. So now the integral test. We'll have the integral from 1 to infinity of x squared e to the negative x cubed dx. Limit as t approaches infinity, integral from 1 to t, x squared e to the negative x cubed dx. We'll need a u substitution. Let's let that be the exponent, negative x cubed. Then the derivative of u, negative 3x squared dx, divide by negative 1/3, and we get x squared dx. From here we can rewrite this a little bit, pull that negative 1/3 out front, limit as t approaches infinity of the integral from 1 to t, e to the u du. That is negative 1/3. Limit t is going to infinity. The integral of e to the u is e to the u. And let's replace that u with negative x cubed. And we are evaluating that from 1 to t. Negative 1/3. Limit. T is going to infinity still. We have e to the negative t cubed minus e to the negative 1. Now if we evaluate that limit, we get negative 1/3 times 0 minus 1 divided by e. And simplifying that, we get 1 divided by 3e. So with that, we know that the series n squared e to the negative n cubed converges. by the integral test. This example is a little bit easier if we recognize that we can start by splitting this up into two different sums. We have the sum of 1 over n cubed plus the sum of 1 over 3 to the n. The sum on the left is simply a p-series. Here p is 3, which is bigger than 1, and we know that that converges. And the sum on the right we can think of as 1 divided by 3 raised to the n. And this one is a geometric series. Here r is 1/3, which is less than 1, which means it also converges. So we have a convergent p-series plus a convergent geometric series, and we know that the sum of convergent series is convergent. So we can say the sum n equals 1 to infinity, 1 divided by n cubed plus 1 divided by 3 to the n is convergent. In this example, notice we have n factorial. Whenever we have factorial, typically we use the ratio test. So we want to take the limit of the next term in the sequence, a sub n plus 1, divided by the current term, a sub n. So we'll start with the top, 3 raised to the n plus 1 times n plus 1 squared divided by n plus 1 factorial. That is the next term in the sequence. And we're going to divide that by the current term, the sequence that we're starting with. 3 to the n squared divided by n factorial. All of that is in the absolute value. From here, we can rewrite it. Limit. We'll copy the top fraction, 3 to the n plus 1 times n plus 1 squared divided by n plus 1 factorial, and multiply by the reciprocal of the denominator, n factorial divided by 3 to the n squared. From here, we can use the exponent rules to rewrite this first numerator. We can think of 3 to the n plus 1 as 3 to the n times 3, and then we'll just copy the n plus 1 squared. In the denominator, n plus 1 factorial, we can also rewrite. We'll write that as n plus 1 times n factorial. And the second fraction we'll just copy. From here we can reduce. Notice that we have n factorial in the numerator and denominator. That will go away. We also have 3 to the n in the top and the bottom. And we have n plus 1 in the top and the bottom. We can pull the constant 3 out front. We have the 3 times the limits of n plus 1 divided by n squared. From here, let's divide the top and the bottom by n squared. Three, limit of 1 divided by n plus 1 divided by n squared, all divided by 1. Evaluating the limit now, we get 3 times 0, which is simply 0. And since that is less than 1, the ratio test tells us that the original converges. So this series converges by the ratio test.